All right, moving along to the wiring devices and connections PowerPoint. A lot of this might be recap for you. Just try to go through it kind of quickly again. We're getting down to the wire here, no pun intended, but um, try to limit a little bit on these PowerPoints as we move forward here, going through the basics. So what we are talking about are the four primary components. We have power supply, which we've already really talked about, transmission, which would be the most of this PowerPoint, what different load options are, and how switching control works, and then a little bit of the general home usage information at the end. Power supply, we already talked about that, so we're going to go through, that's just generation and how that works. So we're going to get into transmission right away. So conductors, that is the device that actually transmits the electrical current within your system. Generally speaking, what we use is copper. It's not too uncommon to see aluminum in different applications as well. Other materials that can be conductors are listed here too, but based on cost and reasonability, copper is one of the best still. When it comes to sizing of the conductors, we deal with the AWG, which is the American wire gauge. So you'll see anything from 40 down to 6. The higher that AWG is, the smaller the wire diameter. And in looking at a couple general code requirements, any 15 amp circuit would require 14 gauge wire at a minimum. Typically, we see this for home lighting, although we could potentially use it for outlets too. Not as typical. Normally, we're talking 20 amp circuits for outlets, but for a 20 amp circuit, we'd have to use 10 gauge wire. Also, you see a lot of lighting on 20 amp as well. A lot of electricians just run an entire house or an entire system with just 12 gauge. And then 30 amp circuits would require 10 gauge. So this would be something for more, in your home, something like stoves, dryers, furnaces, other equipment. You might see something like that. Resistors are different components that add resistance into a circuit. We have fixed resistors, we have variable resistors. The fixed ones change only slightly with temperature, time, or voltage. The variable ones adjust elements within the circuits. So things like dimmers are a good example of variable resistors. Again, I mentioned this in a different PowerPoint, but the wiring itself is an actual resistor, right? So the different gauge wiring creates a resistance that only allows so much amperage to flow through at any given time. So that's typically what we're seeing throughout our systems. We also do use different fixed and variable resistors as well. Different types of wire. SJ cord is just a service cord. Important to understand what some of the nomenclature would be for those. So a lot of times you'll see SJOW on cords. That means it's a service cord. Junior meaning less insulation. O is for oil resistant, and W is for weather approved. So you'll see SJOW on a lot of different cords as you're dealing with them. P is for thermoplastic insulation, and P is for parallel or flat cord. And there's a lot of other ones too that go through the list, but those are just sort of the more typical ones that you'll see. When we're talking about actual types of wiring, when we start seeing 14.3, 14.2, all that kind of stuff, 12.2, what that means is the first number in that is your gauge wire that's required, and 3 is how many insulated conductors we have. So the reason why it's important to understand the insulated is because we also have to have a ground wire. So if it's a 14.3 means we have 3 insulated. That means we'll have a black, a red, and a white wire, and then we'll have 1 bare wire, which would just be our copper ground. So a 14.3 would actually have 4 wires in it, 3 insulated. A 14.2 wire would be 14 gauge wire with 3 total wires, right? 2 of them are insulated, so you have a black and a white. So generally seeing on the jacket here, you'd see the 14.3 with the gauges, what type, right, NM, and then in the testing agency, so like Underwriter Laboratory is UL. Generally speaking, wire ampacity, there's a safety factor just like everything else we have in construction that's built in. So for wire ampacity, we have about a 15% safety factor throughout. The wire size must be increased when the length is a factor as well. So the resistance causes drop in amps. So if we are running things over a really long stretch, that distance has to be considered as well. Generally in a regular commercial type building, it shouldn't be much of an issue. Can be though if you get really big facilities. So individual wire nomenclature, just going through TH, right? Thermoplastic, we mentioned high heat resistance would be H. W is for wet or dry locations. N is nylon coated. So again, these are pretty common as well to see. Then we get into R's and V's and A and S and F and FF. So we have a whole bunch of different things that you might be dealing with or seeing, and there's just a good understanding of what those nomenclatures are and what the abbreviations are. So there's generally three categories of wire sheetings. Conduit is number one here. We got some sort of rigid outer sheet with all the individual wires loosely within. We have cable, which, we talked about SJ cord is actually a cable. We use that a lot in all of our wiring within our buildings, where we have individually insulated wires within a larger insulating sheathing or jacket. And then we have a cord. So a cord is where we have individual wire insulation is the only insulation. So if you think of like a lamp cord or anything that you would typically plug in, you don't really have, you would just have the wires right with that one insulated sleeve around it. So as far as conduits go, in commercial construction, we use a lot of rigid conduit. Can be plastic. A lot of times we'll just be running like a steel pipe for it. But all conduits can only be filled a maximum of 40%. Reason being is once we start having too much amperage, too much voltage going through one specific area, we can create different safety factors. Get too much electromagnetic force taking place, we can get arcing, we can get a lot of other things to happen. So if you ever are testing, using a volt indicator within like your house or anything, and it starts going off when you're close to like a bunch of wires, that's indicating that there's way too much voltage in that one spot. So you probably want to separate those out a little bit. Don't want to start any fires, don't have any problems with that. Let's see here. We also talk about using MC cable a lot. So MC stands for metal clad. We use that a lot in different situations if we need flexibility, but MC cable is not as it's not as protective as your typical rigid conduits, like we mentioned here before, but can be used in a lot of different fashions, not properly rated for some code things. So it's a good way to save some money and time for install, but you can't use it in every application. So example of rigid conduit here, we generally have some sort of lock nuts that have to connect us into different components because we don't want those to get loose. And then metal clad looks something like this, your MC cable. So onto just cables now. What we're looking at here and what we see a lot of is what would be called NM cable, non-metallic cable. Romex is what we generally use, at least in the upper Midwest here. What I see all the time is just Romex, and people just call it Romex now. Very common. So this is when we just have the jacket around the cable. UF cable is an NM cable rated for underground service as well. In your underground service entrance cable, USE, used to connect from the service entrance to a transmission lines. So again, going back to how power is distributed throughout the grid and into buildings and how it's distributed throughout, you can use USE, UF, and then NM cable all throughout that process of transmitting power from one place to the next. Cords I don't really get into much. That's just talking about small appliances, small applications. So again, we have a lamp here. If you see a lamp cord, there you have it. Other transmission components that we need to talk about are cable trays. A tray for cables, right? No rocket science there. But we use cable trays all the time for organizational purposes, making sure that all of our wiring, we use a lot for low voltage as well. As we're running down corridors into different space within our buildings, keeping all of our cables nice and tight in the right spot. So as we're running, if we're not using bus bars for different areas, this is a good way to keep all of our power in one nice organized fashion instead of running power all randomly throughout. So here's an example of what some cable trays would look like, color coded for different things. So if you have data in the middle and power on one side, emergency stuff on the other side, doesn't matter. We can organize it that way. A bus bar, I mentioned that briefly before too, but it's basically it's just a giant conductor. A lot of times you'll see like a copper plate. So something like this would be a bus bar. This does the same exact thing as your copper wiring, just in a lot bigger capacity. So if we have to transmit a lot of power from one place to the next, we use bus bars, and then we step it down from that point into different transformers into different panels for local distribution within your building. Duct bank is a protected pathway for buried electrical cables. So generally we see these underground on the exterior of your building, running into the interior building, but a lot of times they're concrete encased, can be plastic encased, but normally we're talking big concrete encasements or steel encasements. Now we're going to get into boxes. I'm not going to talk too much about that. So we have, different areas call things different, use different terminology. So we have handy boxes or J boxes. This is basically where we need to splice wires, put fixtures, put all that everything else that we need to connect our circuit to whatever that load is. So I'm sure you've seen these before. All have different purposes. The term ganged box is basically the same thing as a J box, except for we have addable or removable sections. So you can also have non-metallic boxes where we can have plastic or PVC or some sort of fiberglass. Very common to use these kind of things too nowadays. We can also have switched boxes too, meant for just receptacles only, or for mounting switches or receptacles. Within our boxes, we do a lot of splicing in the construction industry. So this is where we take all of our circuit and start branching them off and dividing them further or connecting to our loads, whatever those might be. So splicing is just the term for combining two or more wires carrying a current. So this is what we have to do inside our boxes. In a box like this, I can't quite tell if this is metal or not, but we would have to have, it's a little bit of an odd example, but we'd have to have some sort of clamps on each side. This would normally be coming through like a Romex cable or an NM cable. So then we would make sure that stays tight on both ends here as we're connecting and splicing our wires so they can't get loose. Soldering we don't do as much of when it comes to electrical work, more for electronics and low voltage applications. But that's just when we're melting whatever that metal is and combining two things for a permanent connection. Okay, different loads, right, within your building. I think we know what those are, but not just your TVs and refrigerators and lighting. It's also whatever items we plug into the receptacles as well. So different types of receptacles we'll talk about. This is obviously where we're plugging things in, but important to note, different codes require different things. So a lot of our, like a duplex receptacle, duplex just meaning we have two outlets in that one receptacle. If you ever hear like double duplex, triple duplex, that's just, two outlet receptacles. But the break-off tab, I'll show you what that is. So this is a single receptacle in duplex. A break-off tab would be between these two outlets because a lot of different code requires that you wire one outlet one way and the other outlet a different way for lighting purposes. So I thought I had a picture of that. So I'll go back to it. So for instance, in a home in Michigan, anyways, I'm not sure what it is all over the country, but in a living room, for instance, you have to have at least, I think it's one of your outlets wired for lighting purposes for floor lamps. So in that case, maybe it's the bottom one here we want to wire up. So this one would be wired off of our lighting circuit. So when we flip the lights on, this one pops on. But we break off the tab that's between them so that the connection is broken. So this one can be wired into our outlets and the rest of it, so a different circuit. Oh, different faults we have to deal with. So a fault is an abnormality within an electric current. So I'm sure everyone's heard what different faults are, but a short circuit means we have two hot wires that touch, or we have a hot wire, sorry, that touches a neutral or a ground. And what a short circuit means is we have now provided zero resistance to the circuit so that circuit can just run rampant. An open circuit is opposite. It does not allow circuit to flow. So if you hear of an open circuit problem, that means we have infinite resistance and nothing can actually flow. We have an arc fault, which is a high power discharge between two conductors. So this is where that electric current can actually jump from one conductor to the next. So I mentioned that a little bit before. If you have too much resistance in one spot or too much voltage going through one spot at a time and a combination of all that, the electricity wants a place to go always. So if we're not giving it that path, it tries to find its own. So a lot of times it can be caused by that loose wiring, overheating wires, all that. And then we hear ground fall all the time. And ground fall is actually a short circuit, but we hear them used in different situations. Ground fault is when electricity finds its path to ground, right? So it's a form of short circuiting, and then water is what we associate ground faulting all the time because water is a form of ground. So in order to mediate that or mitigate that, we use GFCIs, which are ground fault circuit interrupters. We use those in any places where we have exposure to water. Um, so within your own outlet, then instead of having to go back to the breaker, that outlet alone has its own circuit breaker that shuts off the power immediately to that terminal, breaks the current within that circuit at that device. So that's why we have the resets on them as well. Oh, there's my break off tab. I must have accidentally grabbed it and pulled it in the wrong spot. So here's an example of the break off tab going back a couple slides. I'll try to fix that for you guys before I publish this. But the break off tabs is this little conductor here. So if you break that apart, right, you hook up this nut for one circuit, hook up that nut for a different circuit, it'll work. If we keep that together, then it will not. It'll short your circuit very quickly if we're hooking up two different circuits to the same outlet without breaking off that tab. Okay, then different switching and control, switching and gang boxes. We have, well, it's just an example of what the boxes would look like from what we talked about before. Switch boxes on the left, gang boxes on the right. You can see how we have, it's basically the same thing, it's just we have the ability to add or remove them. So we have different ratings for switches. We have maximum voltage ratings, maximum current ratings, and then the switching action of that individual device. So you'll see SPST, SPDT, and so on and so forth within your plans. What those mean are we have a single pole, single throw, single pole, double throw, double pole, single throw, double pole, double throw. And what that's indicated and represented on plans looks like this. Your pole has to do with how many circuits that device controls, and your throw is how many it is sending that circuit out to, right? So a single pole, single throw is just going from just your single toggle on-off switch, right? Circuit comes in, I break the circuit or I connect the circuit to allow it to keep going. In a single pole double throw, this would be more like a three-way switch where we're changing which direction we're using our energy. Double pole single throw would be something like this, where we have two switches that are each individually controlling their own circuit that are continually moving on once we connect it, and then double pole double throw is combining two SPDTs together. So again, your pole and your throw, right? Your pole is a number of separate circuits a switch controls, right? We're talking either single or double, and then throw is a number of output connections each switch pole can connect its input to. So a single throw is a simple on-off. A double pole has 3 terminals. Looking at an SPST switch, so again, if you're purchasing switches, they have different ratings on them for, again, voltage, current, and whatever our action might be. So this over here is a demonstration what a double pole single throw switch would look like. And the last thing we'll talk about here is home usage, right? So your typical receptacles are running on 120 volts, generally either 15 or 20 amps. Dedicated circuit receptacles may be at 240 volts, 30 to 50 amps. Again, those are for things that are a lot more energy consuming, things like dryers and stoves and refrigerators. Usually what we're talking about when it comes to code is about 8 to 12 receptacles per circuit. It depends on the type of room, depends on the usages. You got to make sure we check the codes because they're all a little bit different. You don't want to be putting too many loads on one circuit. The theory is the different rooms that you have require different amounts of energy consumption throughout your day. And if you look at, if we have a 100 amp panel that's coming into your house, a 20 amp circuit, you can only get 5 of those in your entire house. Well, you have more than 5 because the theory is you're not going to be plugging every single thing into every single outlet or using every single load on each circuit at one time. If you did that, you're blowing fuses or breakers. So again, you should be able to plug in 8-ish, to 10, even 12 here, depending on the use again, but you should be able to plug in and use 8 or so receptacles on a circuit at any given time, given that you're probably not going to be plugging everything else into other circuits at that same time. So your typical lights and switches are normally on 120 volts. They can be on 15 or 20 amps. I didn't mention that too, but code requires 15. Again, usually 8 to 12 lights per circuit, depending on room and usage. Also, now with like LEDs and different low consumption type things, you might be able to get away with a little bit more. But again, follow the code, whatever that might be. And just a reminder, 15 amps requires 14 gauge wire, 20 amps require 12 gauge wire. So most homes are rated for 100 amp main circuit feeds into the panel. A lot of newer homes nowadays are often requiring 200 amp panels. A lot of older homes are getting upgrades to 200 amp panels or bringing in a secondary 100 amp panel. If you think about that alone, without adding to new facilities, new anything else, it should be pretty obvious that we are utilizing a lot more power than we used to, just because you think of all the devices we have that we hook up all the time. So what I would like to make sure that people understand is, even though we're trying to do a lot more electric everything, we're now utilizing so much more power throughout our systems, all throughout that the energy generation plants are operating way beyond capacity that they're supposed to be. So just because things are moving electric doesn't mean we're not consuming more or utilizing less combustion or any of that kind of stuff. It's just shifting where that is. So when you have, when you're looking at how our houses are doubling their requirements, and now we're adding population, adding homes, adding new buildings and other type of businesses, we are consuming a lot more electrical power than we ever have before. Your general homes consume anywhere between 6,000 and 15,000 kilowatt hours per year. Obviously, there's extreme ends where it's even lower or way higher. That's just general throughout the country. It heavily depends on which type of resources you're using. Also, if we have natural gas heating, right, that plays a big role, because that's electric heating is extremely expensive. Electric cooling is extremely even more expensive. Different geographical areas, electricity costs a lot more in some areas than others. If we have moderate climate versus severe climate, right? So I think California is the most moderate overall when it comes to energy consumption, because we have that nicer 60 to 80 degree temperature in a vast majority of the locations, as opposed to like in the Upper Peninsula where we are at Northern, we'd be down to -10, -15, -20 sometimes, rarely, but up to even 100. So those severe climates play a bigger role. So Michigan homes average roughly 10,000 kilowatt hours per year. And I guess that's all I have for that one. So again, if you have any questions, let me know. Got a couple more to go here for you.